Alright, let's get right into it. Today we're going to be covering the triangular case of the moment diagram. Again, we're going to derive it analytically by centroid analysis, and we're also going to show the integration. And then we'll talk briefly about application and kind of summarize some of the concepts that we've talked about over the past, I think now it's 9 videos. So buckle up. We'll go through it pretty quickly, but hopefully slow enough for you guys to understand. So let's draw the condition first. Okay, same sort of loading criteria. We've got Ry, we've got M, we've got length of L, we've got a distributed load where the root or at the wall is equal to W naught. As you know, it's a triangle, so down here that will equal 0. Last video, or a couple videos ago, we went ahead and we defined what is the shear expression for this case. So I'm just going to go ahead and write that on the board. Okay, here we go. V of x given by this function, m given here, ry given here. Where do these come from again? W naught L. W naught times L divided by 2 is the area of the triangle. Therefore, that is equal to the total load, which we can express as a point force, but that's got to be resisted at the wall. Moment, we take that distributed load, express it as a point force. We know that for a triangle, the distance to the centroid is 1/3 the length. So that's going to be this multiplied by 1/3 L. So L over 3. And that gets us to W naught L squared over 6. These are our these are our reaction forces, and that is our shear expression. So again, let's take a cut. But this time, I'm going to take my cut and I'm going to solve this right to left because I do not want to even think about trying to solve it left to right. I could, but then I'm going to have to account for a triangle, a rectangle, a shear. It's going to get disgusting. So let's simplify it. Let's make our expression easier by solving it right to left. All we have to do is change the coordinate. Again, I like to draw shear this direction on this side, moment, shear, and then we know it's going to be a triangle. And that distance is L minus x. So I'd like to always take it from the fixed end. We know this end's never going to move. That ends at x is equal to L. And all we're going to do now is sum our moments. Well, we'll say ML because it's where x is equal to L. It doesn't matter. Label it how you will. Equals to 0. Moment is going counterclockwise, so it's negative. Negative mx. Shear is going to create a counterclockwise moment, right? About this point. It's going that way, or sorry, clockwise. Clockwise is negative. This is clockwise, this is clockwise. Minus v of x. Times L minus x, right? Because L minus x is the distance, not x. You have to be careful here. I almost made that mistake just now. So negative because it's clockwise, negative because it's clockwise. The body force acts counterclockwise, right? Because it's going down, and about this pivot, that distance is going to be going in this direction. So we're going to add, but now what is our expression for the body force? Well, I have W naught divided by L. That's going to be how much this changes over time. And then we multiply by L minus x. Right? So when x is equal to 0, we have the full amount, W naught. When x is equal to L, we have L minus L is 0, so this term goes to 0. So this right here is our expression for this height. We then have to multiply by L minus x over 2, because again, height and then base and 1/2. That right there is what gives us our force. But now we need to multiply by the distance to our point. And we know that a triangle is 1/3 from the tall side, from the part that has the, just from the tall side. So that means it's going to be 2/3 from that little tip. So we multiply by L minus X, but 2/3 L minus X. And this here is our expression for the body force. Have we accounted for everything? Okay? We've accounted for the shear, we've accounted for the moment, we've accounted for the body force, there's nothing else happening. This here is a proper expression. Now, in order to solve this, you're going to have to expand it. And you're going to see it's going to get quite nasty, because this here is going to turn into a cubic function. This here is a quadratic, but it's got 3 terms, and this here is going to elevate part of that to be a cubic. But also, you're going to end up with 6 terms, v of x and L minus x. You're going to end up with 6 terms here. That's 12 terms. It's going to be quite a lot. You can do it by hand, and you're going to notice everything's going to start to cancel out. It's going to get nice and pretty. But all we do now, we move this to the other side. M of x equals, and again, I'm not going to do the math. You guys can do math. You guys can all do algebra. But if you do the algebra here, and I encourage you to do so, because I might have made a mistake. I say the probability that I got this correct is 99%, not 99.9, because it is a little more complicated. But I'm very confident in my answer. You can do the math and solve it out for a final expression, simplified down to this. And again, if you guys do the math and you think this is wrong, comment down below. Extra bonus points if you catch a mistake, though I am quite confident in the answer. Why am I confident? Because it satisfies my boundary conditions. If I go ahead and I set x is equal to 0 in this expression, I end up with just this term, which again, the way I've defined it, moment is going in this direction, which means it has to be going in this direction here. So again, that works out perfectly fine. What else? Okay, so I'm confident in this answer because I know my boundary conditions. I've drawn moment this way. It flips sign at the wall. W naught L squared over 6 is exactly equal to the moment resisted at the wall. Add x is equal to L. You guys can do the math here, but it's going to cancel. We're going to end up with W naught L squared over 6, W naught L squared over 2, W naught L squared over 2. These two terms will directly cancel. This term over here, W naught L squared over 6, will cancel with that front term. It goes to 0. So I'm quite confident in the answer. And again, the way we solve this is by analytically determining what the loads were and how they created moments by point force analysis and centroidal analysis. All of the things that we've talked about taking a distributed load into a point force, it all matters. That's the thing with structural engineering, is all the concepts kind of build off of each other. You can't skip your fundamentals, which is why I think this lecture series is very important for all of you. So there we go. We've come up with an expression for moment. We could graph this, but also remember, moment is simply the integral of shear with boundary conditions. So we should be able, as another sanity check, but also if you wanted to save time and not do this ridiculous 12-term expansion, you could have solved it by integrating with boundary conditions. So real quick, if we were to do that, all we're doing is we're integrating W naught x squared over 2L minus W naught x plus W naught L over 2. If we integrate this expression over here, we're going to get to one that looks like this. As you can see, it's already identical here, 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 and then when we do our boundary conditions on C, remember, you should always do both boundary conditions. It helps you validate your signs. But when we do the boundary condition on C, we're going to realize that C has to equal negative W naught L squared over 6, which is going to validate our entire equation. And that's how we solve it, by integration with boundary conditions. And you're like, wow, that's a lot faster, and it is. So if you want to analytically understand, and I encourage you guys to always tackle it from this perspective if you have the time, you can analytically and really understand what's happening. But if you're on a test, you're in a time crunch, you want to get it done, well, you go ahead and just integrate the function. And it gets you the same answer, but again, this is less conceptual than this method. So whenever you're doing something for the club and you're trying to analyze what's happening, I will always say, do it this way. Because by doing it this way, you are going to conceptually understand what your loading criteria is. And then you're not going to make a simple mistake and then not know where it came from. If you do it this way and you make a mistake in your integration, you make a mistake somewhere else, your C term might cancel everything out, but the function might be wrong. This way, it takes longer, but you can be more sure of your answer. So here we go. Now we can go ahead and, of course, we can graph this. Okay, same thing as before. So over here, we're at W naught L squared over 6. Over here, we're at 0, and it's going to be cubic. So it's going to look something like that. And again, if you wanted that additional level of accuracy, you could solve for a point. If you're doing it for the club, you're going to plot this in MATLAB, technically. So you just plug the function into MATLAB and put in a bunch of different x values from 0 to L, and you get the curve. But by hand, this is good enough. All this does is it tells us, hey, the max is here at the wall, as expected. Okay, so let's go ahead and talk about a few more cases real fast, just so you guys aren't super confused if something like this happens. Now I always do the cantilever beam, but again, this just has a unique set of boundary conditions. I know this free end has to be 0 for shear and for moment, and at the wall it has to equal Ry or has to equal M. Now you might see examples where you have some sort of distributed load, like that. You might see a point force load, you might see a point force moment, that's how they'll draw it. All of this stuff. And again, just like I said for shear, think about it analytically and you're going to be fine. Again, a distributed load will cause a moment that varies as a function of x. If it's a constant distributed, like a rectangular load, you get a linear moment. If it is, sorry, take that back. If it is a constant rectangular load, you get a quadratic moment. If it is a triangular load, you get a cubic moment, etc. If there's nothing happening in a region where there's just no forces applied, it's going to be constant. Nothing is changing. Whatever the max value at the end of your distributed was, it's not going to change in this region. Right here, we have a sudden point force applied. A point force, if I'm moving left to right here, it's going to shock my system. It's going to cause it to jump. Because all of a sudden there's nothing, then there's something, and it's something times a distance. It's going to be quite large. So that's going to cause a discontinuity of sorts. It's going to cause a jump in your graph. And if you have an applied moment, then you simply take that into consideration. It's like you have an applied force. Remember, if I have an applied force, I have to multiply by a distance. If I have an applied moment, I just take it into consideration. So if I were to basically, let's say I plot this, roughly speaking, I expect a quadratic function there, and it's all going down. This one is going in this direction. That might change it. Let me think real quick. Oh, good. Yeah, so that's going to jump it that way. So we might see something like, okay, it's quadratic, then it's constant, then it jumps, and then it is constant for a little bit, and then it jumps again. We might see something that looks sort of like that. I haven't solved this out in its entirety, but you can do all of that. As long as you keep track of your directions, just take a discontinuous function, define your moment equation, moment balance for this section, then do it constant here, then define it at this point, and then define it at that point. You're good to go. It's not any additional level of complication as long as you understand how to break this down by taking that cut and exposing those internal forces. And we've talked about that a lot. I'm confident you guys can do this. So if you understand the key concepts in the centroid analysis that I've talked about, this is not any more difficult. So again, why do we care? Why do we care about moments? Well, we're going to talk about it down the road here in a couple more videos. But when you're analyzing your internal situation inside of your wing, inside of your beam, inside of your structure, they're going to have different strains and stresses and effects that are caused on your member by these forces and moments. So you need to know how to calculate a force and moment at any point. Typically, again, the maximum force or moment that the thing can experience. And that's going to allow you to determine what your stresses and strains, and we haven't talked about those yet, but those are what characterize how your material behaves, how strong your material is. You basically standardize all of these forces by unit area, by Young's modulus of elasticity. We'll talk about it. Okay, it's going to be exciting. But you can standardize all of it by those values, and as long as you know what those values are, you can determine if your structure is strong enough. Now in future videos, actually hopefully next video or soon after, we're going to talk about the summer composites test. It's been mentioned a lot this year. Oh, we had a team that investigated composites over the summer, blah, blah, blah. Read the report. I'm going to walk you guys through the report and why we did what we did. Because oftentimes you're not going to have values and parameters for your materials because you might be combining them in different ways, using unique shapes. You need some sort of way to analytically determine if it can hold weight, if it can support a load. And that's what we did over the summer. Yeah. So anyway, we're going to hopefully be discussing that composites report in a future video, hopefully next video. But again, I just wanted to throw up some concepts that we've covered throughout these past 9 videos. These concepts here are the core for what you're going to do when you do any sort of structural analysis. Remember, 6 equations. By static equilibrium, if it's not moving, sum of forces are 0, sum of moments are 0. We learned about a point force. We learned how to take a distributed force, turn it into a point force, and then apply it at the centroid to create moments. These concepts are all linked. We then applied it to shear and bending moment diagrams, which allow us to determine where the maximum shear or the maximum bending moment is experienced by our structure. All of these concepts are crucial. It allows you to make a lot of engineering assumptions, or it allows you to characterize your structural design. I like to think of this as giving you a physical way to prove intuition. Okay, let's take a couple of examples. Let's say we're designing a tail for the plane, right? We designed a tail. Should I have 1 bar go to a tail, or should I have 2 bars go to the tail? Now, obviously you guys know we had 2 bars going to the tail, but why? Well, because any sort of moment about this axis, right? About the axis, so let's say that the tail is coming out of the page like this. Here are the 2 rods, right here. Any sort of twisting in this direction, if I just have 1 bar, it has to be resisted by the torque. So the bar actually physically has to resist this torque. But if I have 2 bars, then because they're fixed here, there's a little bit of a moment that's resisted in that direction. Not to mention that if you try to pull it in any other direction, you've got double the support. So this allows us to resist moments, right? That's why we made that choice. There's a great comment last video by Kaylee about the wing. If we draw the wing, remember the wing is just a cantilever beam supported in the middle of both sides. Cantilever, cantilever. She commented, well, yeah, we were making a continuous piece of balsa wood through the middle, and now you guys know why. If we have a continuous piece of wood, this allows us to have a continuity going through the area which has the highest shear and the highest bending moment. That allows us to make sure our structure is as strong as possible in this area. We don't want discontinuities. We don't want any seams, any cuts. We need that to be as strong as possible. We don't really care out here because this is not supporting the load. So I can have a bunch of different smaller pieces. It doesn't matter. I don't care about these little cracks because they're out near the tip where there's basically no load applied. But in here, it needs to be strong. So why did we slot the wing then? Remember? We had a giant hole cut in the wing there, which weakened this central part of the wing. That choice while a poor one structurally allowed us to do certain things with design. So we had to make that choice. But notice, we cut it out of the side profile of the wing. We cut basically into here. All of this stuff is rather thin. It's not contributing to the main strength of the wing. The main strength of the wing comes from this thick leading edge and center portion of the wing. So instead of cutting this away, we cut this part away. Not as important. So again, we take certain liberties, but we do have to work with other constraints. But we do work with the constraints in such a way that it minimizes the effect. I'm not going to cut this portion of the wing away. That's the strongest part of the wing. I need that. Which is why our carbon fiber rods in the wing went right through there to support that strongest area, that area that takes the most load. When we talk about the summer composites report, we're going to talk about how we know this takes the most load too, just by watching. A lot of interesting points coming up, but what I want you guys to do is really think about all of the choices that were made in structural design this year that we haven't really talked about. Like, we never talked about, oh, let's put 2 bars. We just said we're putting 2 bars in the tail. We never talked about, let's put 2 bars in the wing. We just said we were going to do it. But now you guys understand why, right? Why did we do 2 bars in the wing? Why 2 bars in the tail? Also, why 4 in the fuselage? That's something to think about as well. Why did we put 4? Think about what's attached to the fuselage, right? We have gear, we have a wing, we've got a nose, we got tail. Why did we choose 4 bars? And if you think about what's being attached, you guys might be able to realize why 4, not 3, and certainly not 2. So yeah, hopefully this all makes some sense. Again, leave a comment if you have any questions, DM me, chat with me. I want to talk you guys through this because next year we're going back into conceptual design, and if you guys have this down, we can make better design choices and come up with a better plane. So again, it's been fun, these past 9 videos. We'll make a couple more, talking about stresses and strains and other fun concepts. But there you go. This is a summary of AA210 statics, engineering statics, explained from a practical perspective. Hopefully it's been informative. Thank you for watching.